Today we're tackling two different topics, and for the first one, let's assume I have some settings data, not settings, settings data. It doesn't really matter what's in there right now. Say 100 bytes of data, and I want to securely store them on my hard drive, or maybe my player's hard drives. But I don't want to make it too easy to modify, because changing save states is an easy way to cheat, which in of itself, at least a single player game, doesn't bother me, but maybe there are also some dangerous settings in there that could break their system, and you don't want to make it too easy for people to just play around with your stuff for whatever reason. In that case, we want to make it a bit harder and obfuscate the data that we store somehow. And one way to go about that is, instead of just, let's see, we make a file stream, and why is it not reacting? Something is broken. Let me just reopen this again. That looks better. File stream. Yeah, that looks better. Okay. So we would have a using statement, of course. And then file stream dot. We can make this easy, right? Settings 0 single store length, like that. And this would store the settings somewhere. Some path. Create, we need to write access, and let's say no shared data. Right, this will just take our byte array, which doesn't really contain anything, but it's there, and would write that out to a file called some path, and data is stored. And to obfuscate this, we're using a very simple mask and apply an XOR. Which is just obfuscating, by the way. Don't get the wrong idea, this is not secure in any way, so this is not a way to encrypt your data. So don't put passwords or anything in there. It's just to make it a bit harder for people to just directly read it. A bit more annoying, at least. And while I could do that to our settings before storing it, I might want to store the settings in different parts of my code, in different contexts. Or I have other things that I want to store and obfuscate as well. So instead of writing the code one time in here, I'm creating a very special stream for that. So we're just going to make a new class. Stream. And we're going to make our life a bit easier and just inherit from file stream. So we just extend basically the normal file stream, so that we can use obfuscated stream as a file stream, including everything a file stream can do. We just modify the way it handles the data. And let's just add an constructor. I'm currently choosing which one to use. Let's take this one. I think that's the one I used. Yeah, let's go with that one. And let's make it a constant byte mask, which will be, I don't know, 1, 2, 3. And why is it not typing? Why is it not typing? 1, 2, 3. Keyboard settings. All right. So what we can do now is overwrite the write method. Overwrite. Actually, can I? Does it have the autocomplete? Does it have this one? It does. Cool. So as you can see, I'm overwriting the write method of the file stream. And internally, we are gonna refer to the base class again when we want to actually store the data. We're just gonna change this content before we pass it on. And maybe we want to not change the actual byte array, because someone else might be using it, so let's create a new byte array for that. Get a new obfuscated will be a new byte array with the same length as buffer. And then we're gonna go through the entire array, the entire buffer array, byte by byte, make an exclusive OR with the mask, and then store that in the same position in the obfuscate array. And I'm gonna try and be clever here, which always works out great. Let's see, we start at offset plus count -1. Then as long as I is greater or equal to offset, because we're gonna go backwards in this array. This way I don't have to include any calculations in my condition here, or any other variables for the offset. And this is not necessary. I'm trying to make this efficient, kind of, but only while fitting my personal statics. So this isn't actually a good way to program. It's just the way I do it now. And he's complaining because this is not a byte. Because the XOR converts that into an integer, and then we have to just cast it down back to a byte, store that in obfuscated, and down here we pass on obfuscated. Admittedly, we could have actually simplified this a bit more. I mean, if we take this step to create a new array, we could also limit this new array to the size we copy. So I copied the entire buffer, but if these variables are used not to store the entire thing, we could actually limit it to just count and then copy only that part, and it's just doesn't matter. So actually this kind of doesn't really matter anymore. Anyway, let's override the read method as well. Let's take the straightforward one. And we're gonna rename this. Read, we're gonna create another array obfuscated, just like in the write method. And we're gonna read into this obfuscated buffer. Gonna keep everything the same. We don't really care about the return value. I'm gonna copy this loop, because that's what we want to do as well. Just this will be obfuscated this time, and this will be the buffer. Because it's an XOR, just applying it once will obfuscate it, and if we apply the same mask again to the obfuscated one, we get the original back. And then return. Oh no, we don't return. I mean, yeah, we return as well. Guess we need to store it after all. Red bytes equals, when we return red bytes, but buffer is already overwritten. All right. So with this, we have an obfuscated stream. A stream which behaves like a file stream. Only that internally, when we write or read the data, it will, before writing or after reading, apply this bit mask to obfuscate or deobfuscate the actual data. Which makes it a bit more annoying for people to figure out what the settings are. Again, this is not a way to encrypt the data at all. Like, this is super easy to crack. Or not even crack, this is not something a determined person would not be able to figure out in an hour at most. Okay, so this is just to annoy some people and to whittle down the number of people that can actually just fiddle with your data. And it's an example of something you might do. For example, you could actually figure out an encryption algorithm in here. If you do that, that's still not a good idea because there are already encryption libraries out there, and you should use the ones that exist and are proven to work instead of writing your own one that most certainly will have a couple of security flaws, but different story. What we did here was extend the FileStream class to just add our own functionality in there. But this practice could actually be filed under an umbrella of patterns called wrapper. Could, sort of. At least I've seen it written that way or described that way, that this would fulfill criteria for the decorator pattern. As in, we're taking the file stream and, well, honestly, we're not actually decorating that much, we're just changing its behavior. What we probably should have done was public void write and just byte array buffer. Then write buffer. Oh, wait, 0 buffer.length. Like that. And then for read the same, just for reading out stuff. And then we definitely have decoration and sense that we add additional stuff to decorate the stream with. We have our old stuff, but we changed the behavior, and we even have our own method to interact with things without writing it out like this. Which, yeah, is a type of pattern you've already used a couple of times by now, and you're not even aware that you're using a pattern. Because patterns aren't really all that special, they are just descriptions of things you often do just naturally. Because they're a good idea. Personally, I'm still somewhat bothered by this. Because right now I'm stuck with file stream. Which so far was great. I'm just using it to store data on my hard disk, or SSD or wherever, or read it from there. But I might want to expand my game a bit. Maybe I want to not store the data on my disk. Maybe I want to upload it somewhere. Or just send it through the network. Or maybe I want to stack other types of streams in between. Maybe I do want to have an actual encryption, or maybe a compression if this is rather big. And right now the obfuscation can only happen for file streams. That's very limiting. But talking about obfuscation, talking about encryption, when I demonstrated the existing library streams for encryption and compression and all that, when we use them in a very special way. And we can do that in here as well. So let's just obfuscated stream. Let's rename this. This is not an obfuscated stream, this is an obfuscated file stream. Like that. Let's rename this as well. Let's create a new class. This one is going to be obfuscated stream, but this one is actually just a stream. And we're going to inherit from stream again, but only stream, not file stream. And the next part becomes very easy because of my tooling. Yes, please. And what we've done now is let's just call it stream internally and initialize it from constructor. What I've done here is I'm overriding all these stream methods. I'm providing a fully working stream. Fully functional, regular stream class. Only every single call is internally just redirected to the same call on another stream. Whatever stream that is. Actually, we could stack several obfuscated streams, so this might be another obfuscated stream, which internally has another obfuscated stream. Doesn't matter, it's just a stream. And we know, since it's a stream, it will have these methods because they are standard stream methods. And we can redirect every single one of these standard methods calls to another stream implementation. Actually, let me just quickly sort this. That's better. Properties to the top. And what we can do now, instead of an obfuscated file stream, can return this to just file stream. That was too much. Come on. File stream. File stream. Didn't have to really change anything in here because the obfuscated file stream was just another file stream. And in here, we're now creating a new actually obfuscated stream, which will get a file stream. Actually, let's put that in the using. And this will now get this. And this write method is actually not quite right. I mean, it's working just fine, just it's not the right method we define ourselves. Okay. Actually, we don't need those either. This is exactly what we did for the encryption streams or the crypto streams and the compression gzip streams. We basically have some stream of our own, any type of stream, and we pass that on to a new instance of this special type of stream. And everything we do will be redirected through this special stream and only then end up in our original stream. So right now, as it is, this stream isn't doing anything different than file stream. It's just a layer on top and just a form of abstraction, but it's not changing the behavior in any way. But this allows us to interfere with the behavior without changing the original stream. What we created here is what I consider an actual wrapper. And I think this type of wrapper would be called a proxy. And it's a proxy because this stream accepts calls and forwards them to be executed on another stream on your behalf. If I have an obfuscated stream right now, I don't have any access to the actual file stream. If I have another method, static void write settings, and I get maybe a stream, and byte array settings, like that. Maybe this is part of my library somewhere. And just copy this out. This will be stream, not the file stream anymore. And then in here, write settings, file stream, not the one, settings. So in this method in here, I get the obfuscated, get the original stream and an obfuscated stream. Actually, this was the wrong way to go about this. Let me correct that. This is not demonstrating what I wanted at all. File stream. And this gets the obfuscated stream. Now this is what I actually wanted. So we have file stream that's backing an obfuscated stream. And what the rest of my code gets is just this obfuscated stream. Just in form of a stream. I could convert this now. I could cast it to stream, say to an obfuscated stream safely, but that's it. In this method, I have no way of accessing this file stream. Well, again, with the exception of reflections, because reflections break all rules. So we can safely exclude them whenever I say you can't do that. Just always assume reflections can do it because they break all the rules. So when something doesn't work, it's because it doesn't work except for reflections. So yeah, this stream hides effectively the original stream, and we have to go through our obfuscated stream, which we can now use to our advantage by essentially copying these two methods. So first, actually you can straight up copy them. Read and write. Just put it in here. The write method can go. The only difference is that we don't refer to the method in our base class. We actually call on a different instance. And I forgot the mask. Like that. Yep, that works. I don't need a primary constructor. Yeah, let's make this read-only as well. So we now change the behavior that forces the system to use our obfuscation without any way to directly access the stream below it. So the obfuscation is always happening as intended. But I don't have any other way to directly access the stream, which means I have no way getting around the obfuscation. But because this obfuscated stream itself doesn't ask for file stream, I can do something else as well. Instead of file stream, this might be some network stream or memory stream. I mean, I'm just pushing data around in memory. Or it could be a crypto stream or compression gzip stream, zip stream, whatever you have. As a proxy, we can direct or we can influence how the system is used or how the actual data is used, underlying implementation. And it also allows us to limit access in a way. So for example, I might not want this method to actually write anything. I mean, it's the right method, so that would be an error, but that's good. If it's an error later on, if we get an exception, then the programmer knows they messed up and has to fix it. They have to fix it. And by using the proxy, we can prevent them from actually writing. Simply changing this, for example, to false, can write. So they know it's not possible. And we can change this to exception, throw new, let's call it invalid operation exception, read only. Let's just copy the throw because we're going to use it a couple of other times. So if I'm changing, no, actually position is fine. No, that would be seeking. Sorry, changing position is okay. Flush doesn't make sense. We can just leave it out. Flush is called anyway. Let's ignore that. Seek is fine. Set length would be write operation. And of course, write would be write operation. Right. So reading, seeking, that's fine. But anything that would change the underlying stream is now throwing an exception. So this obfuscated stream is now read-only, even though a file stream would be writable. At least our file stream is configured to allow writing. It's actually configured to only allow writing. We can't read. So this special constellation doesn't make too much sense, but it's possible. This method, even though this file stream that's backing everything up is what we're interacting with, is writable. The stream I get wraps this file stream and prevents us from getting access to those functions, to those features of the file stream. The proxy handles all our requests and expressly forbids us from accessing certain parts of it. We can also go the other route. This file stream, as mentioned, is only for writing currently. Can only write. We don't have any read access. So reading would lead to an error. But because it's a proxy, we could just determine that, hey, for reading, if stream.can read, not. Actually, let's get the old code back. If not, stream.can read. Oh, then just return 0. That's fine. So instead of throwing an exception, I'm doing something that's forbidden. I'm just gonna say we didn't read anything. Which is possible. Can read, yeah, let's say it's always true. That's fine. So even though our file stream cannot be read from, we allow it. This stream I get down here, I could get a read method to work without exceptions. It doesn't deliver any data, but it's not breaking anything. And at the same time, while this file stream expressly allows to write, we're wrapping it in our obfuscated stream, in our proxy, and prevent anyone from writing. It's a very simple concept, but it's very useful in many cases. Especially when you're not too sure what stream you have and you want to make sure that you have certain capabilities. Even if it's just some fallback value that you get. As long as it's not breaking anything, that's fine. Let's say you have a piece of code that can get different streams, and most of them do actually something useful, but in the off chance that you get one of the rare streams that don't fully allow these things you want to do, by using the proxy you can implement a default behavior in any case. So this type of wrapper, very useful. Let's change topics. Let's talk about the settings byte array. Where does it come from? How do we get a settings byte array? What are my settings actually? Let's start there. Let's just let's make a record. That's what I think I used so far. My examples. Let's see. We had. Oh wait, standard record. Just put it in here. We had an int frames per second. We string. Say server address. Second for server address. Bool. Single player. Only. So maybe it's a multiplayer game that people can join in while you're playing, and you want to turn that off, so you can change this setting. Yeah, like that. So this would be the settings record. Of course, you could also use a struct or a class. In the end, doesn't really matter. So this would be the actual settings. So we have new settings. Let's say 60 frames. Localhost. I don't have any specific address. Closed. Let's not think about that. And true. Makes more sense in that combination. I don't have a specific address to connect to, so it's only for single player attention. So let me drink something. Alright. These settings, think about for a moment how these are stored in my program and how they are stored inside the computer. And that is great, my screen share turned off. Let's try again. Yes, please connect. Some visual aids. And the entire program shut down, which is a good sign, I guess. Let's try that once more. Accept. Don't tell me if these servers are down. Alright, I guess no visual aids today. Doesn't make me very happy. So, guess we'll do it the old-fashioned way of just explaining. So I tested this before the stream. Everything worked perfectly. And then without me doing anything, the program just gives up, which hasn't happened before. Like not starting? Sure, that hasn't happened. But breaking down while running? That's new to me. Not for this software, at least. Alright. Well. Memory. How the data is stored. We're using a record right now, which means we use a reference type. So the settings object is just an address on the stack, and the actual data is on the heap. And actually it's scattered all over. The frames per second and the single player only, those are value types, int and bool. So they can be stored just directly as a full value. They're still stored in the heap in the area where we store the settings instance, but they're at least there. String is a reference type. It's a very special reference type, but it's a reference type, so that's just an address that points to somewhere else in our code. I think it's also part of the heap. I'm not too sure if they still count that as... It should be part of the heap still. Honestly, I'm not too sure how .NET handles strings. Or if that's stored somewhere else in a special type of memory that they don't regard as part of the heap. No, details, that doesn't matter. When we want to store all these settings in a file on our hard drive, we're not storing a complete dump of our program memory. That doesn't make sense. That's just our running program. What we do want to do is store these specific values. This integer value, this boolean, and this string. And we put them somehow together into a single file on our hard drive. To do that, we need to convert them into a series of ones and zeros, which we then pass on to Windows as please store these for us under this address on your disk system, domain storage. To do that, we use a feature called serialization. We serialize this settings instance. We take all this data that's stored in settings and we think of a way we can represent this data as pure ones and zeros. And we have all the freedom in here we want. In the end, what we want is just a sequence of ones and zeros, ideally in multiples of 8, so we get full bytes. And that's how we get a byte array that we can pass on to a file stream to be stored, for example. Of course, there are other ways you can store the data. You could, instead of converting this into ones and zeros directly, convert this, for example, into text. And then store that text on your hard drive. Though that is a bit of a cheat method because that text isn't stored as text, it's again stored as ones and zeros. It's just when we store text, the computer can already do this conversion to ones and zeros. That makes sense, and puts those on the hard disk. And when we want to read the data again, it will read those ones and zeros and convert that to text, and then we get the text and can do something with it. So we can, for example, use pre-existing serializers. One of the options is a Json serializer. There's one in .NET now, in the text.json namespace. Otherwise, Newtonsoft is a pretty known library or company or project. Let's see, was Newtonsoft owned by some? So the Newtonsoft libraries were pretty popular before. They are still popular, I think. It's just now we have a built-in JSON serializer. There's also XML serializers, which was already supported in C# and these standard system libraries before. Those are popular choices that can, for the most part, just be used directly. So JSON serializer dot serialize. Actually, you could make it easier. No. You can give it serialize. We can put the settings directly in here without some kind of compromise. So the settings themselves have to be a very simple construct, because the standard serializers do expect certain abilities when they modify the data. For example, they look through the properties or fields and just try to go, okay, this is a data type I understand, that I know, and I know how to handle. I'm going to convert this into a JSON string, for example, or JSON integer in this case, because JSON supports integers directly. and this is a string, which I know, and this is a boolean, which I know. But if I had something like our obfuscated stream, which itself, okay, doesn't make too much sense because it's not data, but if we had custom class in here, custom type, the default libraries wouldn't know how to handle that directly. We would have to somehow teach them how to convert custom types that we defined by providing additional code specifically for serializing that one type. And those are options we can add, and that works differently for each library. I'm not going to do that here. But ideally, in the simplest case, it can understand our type, directly serialize it into a string, and on the flip side, it can also convert that back. We deserialize. And again, it expects things to be rather easy to understood. And we get our original object back, at least in terms of values. This is of course a different instance, but if I'm just gonna run this code now. This is our original settings object. Let's go to locals better. So original settings, 16 localhost and true. Deserialized is also 16 localhost and true. And if we look at the serialized text, can you see that window? No? Let's just copy that out quickly. That's the wrong keyword again, like that. This is what we have in there. A fully featured valid JSON string. This is what JSON looks like if you're not familiar with JSON. We have different keys here and a matching value for each of them. And these can be more complex. We can also have data structures in here that hold values. Like lists, arrays, whatever, dictionaries. But they can also be very simple, like this one, where it's straightforward, just a couple of named values and that's it. And it would be very similar if you used the JSON, an XML serializer and deserializer. This would be just an XML format. But again, standard libraries that do that already. Whether you use JSON or XML, it's a matter of taste. So there are already pre-existing formats, and this is now a string you could just directly store on your file system. JSON serializer also has the whole, what was it? Where is it? Serialize to UTF-8 bytes. I pass on the settings here. I actually get a byte array. And it does so by converting this string into a byte array using the UTF-8 format. We talked about encoding formats before. That's what would happen with this string if you just use the file writer or just file write all text or something to store that on a disk. It would convert that using one of the encoding formats, one of the standard Unicode systems, unless you specify one yourself, and write that to disk. And with this we can get the bytes directly and put it directly in a file stream. All of this is very convenient, and for something like a record, perfect. Like a record is like it's built for it. It just works straight out of the box. Very reliable. But can be a pain if you have very unique features you need to take care of. Like very specific types that you have to handle, or very specific ways this class is internally constructed. For example, these are right now straight up fields which directly contain a value, but maybe the properties in your class or fields have connections between them. They interrelate or maybe just reference one another. And at that point you have to specify that certain properties are supposed to be ignored and others are to be serialized. And maybe you want to serialize them a certain way that's different from the standard way you usually would do things. And then you have to change the serializer by defining your own code, your own behavior. And it's like, it's a trade-off where The standard case like this is super easy, straightforward, works great. But if you have any unique case, it becomes very complicated very quickly. I'm exaggerating, I guess, a bit, but as long as you do standard stuff, just use these standard libraries. Works perfectly fine. If you have something more specific, look up how your specific library of choice handles that, and if you feel like it's a lot of work to do all of this, maybe think of making your own serializer, which is what we're going to do now. Because serialization itself is pretty easy. I mean, you have seen how the JSON string looks, right? Very straightforward string. And you could write your own JSON serializer if you wanted. At least for simple cases, they are straightforward. We've already looked at reflections. You can use reflections to read just all the different fields and properties and put them in straightforward list of strings that you store as text. So with reflections, you can very easily write a very generalized serializer. What I want to do is write a very specific serializer for settings. And what I'm going to do is I'm going to put that serializer in settings. I want to have a method in here, public byte serialize, that I can call, that will give me a byte array that contains this settings object, for instance, as a byte array. And on the flip side, public static settings, deserialize, yes, and this one will get a byte array. Let's call it like that. So if I have an instance, I can call serialize. .serialize. And on the flip side, I can then call settings.deserialize, serialize, which will get me a new settings object. And the specific way we serialize and deserialize is completely up to you. You have absolute freedom in this. All that matters is that you create a byte array that you can convert back to the original data. So you have to think of some way to store the data in a way that's stable enough to read back out in its entirety. One convenient class that you will run across is bitconverter, because that already contains a bunch of really useful methods like get bytes that you can plug in data like frames per second, and it will give you a byte array that represents this object. And you can do that because these types are very simple. I mean, an integer is just 4 bytes, straight up a sequence of 4 bytes, 32 bits. And this will basically just give you 4 bytes, a total of 32 bits that match exactly the same sequence of ones and zeros that we already store in memory. So very straightforward, very direct. For the bool, we can do the same. This would be FPS bytes. This would be 3 bytes. Single player only. And for the server address, a string, there is a slightly different way. The same way we did it for JSON, or talked about it for the JSON class. We use an existing encoding format. And I always default UTF-8. We use get bytes in there and get the server address bytes. And that way we have 3 different byte arrays that each represent one value in our settings instance. And we can now combine them into one large byte array. And let's go for the straightforward method first, because there's a little thing we have to address here. So, serialized. It's a new byte array, and it's the total length of FPS bytes plus address bytes plus, not S bytes, SP bytes. the it's uppercase E. Dot length, of course. My bad. Length. Dot length. Dot length. It's way too hot in here. Length. And we will return this, serialized. And to copy the data in, we use the array class, which has a nifty little copy method that will copy all the data over and is pretty performant. So serialized will copy first FPF bytes, starting at 0. We'll copy that into serialized, starting at 0, and we'll copy FPF bytes dot length. Though we already know this length is going to be 4, so we could also shortcut this. But this way it's just a bit more flexible. But again, it's directly referenced to this integer. We know it is 4 bytes. If it's anything other than 4, something went wrong. But we just leave it open like this with the length to be not limited to very specific size. And we do something similar for the other two. Copy the address bytes and the single player bytes into serialized. Only this time we have to do bit calculation. Next. And then we're gonna increase index to length like this. Because the copy method will not put the address bytes, of course, in the first few bytes and the first 4 bytes of our serialized byte array. That's where we store the FPS bytes. So we have to move a bit forward. And that's not index, sorry. That was index. And that's FPF bytes dot length. Dot length? Why isn't it working? That's better. And then we do the same for the address bytes, increase this. Address bytes. This is single player bytes, index, like that. Okay. So we copy the FPF bytes at the first position on our array, and then we basically move the head, the index, forward by total amount of bytes we have already written, which is 4. Actually, does it return anything by chance? Copy? Ah, still doesn't return anything. Whatever. And then we copy over the address bytes. And again, increase the index, so we know where to write the single player bytes. And this is how we serialize the settings. At least that's how we would like to do it. There's a little problem that we come across when we try to deserialize again. We can use bit converter to convert bytes into an integer, for example. So we can use this method toInt32 to revert the exact same operation that we did with get bytes on our integer here. This will take the first 4 bytes and convert that to an integer. That works. So we can do this, and that's FPS. And we can do the same with the Boolean. Single player. And we can use encoding.utf8 to string. No, not get string. Get string. To get the address. The issue we have now is only the first couple of bytes are meant for the FPS, and the next few bytes are meant for the address, and only the last bytes for the boolean, or last byte specifically. For FPS, we at least know it's only taking the first 4. We know that for sure because it's an integer. How many bytes is this gonna take? And we can cheat a bit. We know that we're only gonna start at 4. And to know how many bytes we take, well, we know that this is a boolean that takes only 1 byte. That's all we need. We can't limit it to just 1 bit. So we have to take at least a whole byte, but only 1 byte at least. So this will take 4 bytes. This will take 1. So the total length will be 5 plus however long this address is. So we can do serialized settings.length minus 5. And that's how many we will take from there. And then we can do here the same with the start index, which is settings.length minus 1. And then we can return a new settings object. Yes, address and our boolean. Now this should technically work, and let's just verify that it does. So if we compare the original to the deserialized one, looks like it worked out. If you're curious, here are the bytes that we stored. The first 4 here are our integer. You can see the first byte contains the 60, because it's just still a 60, which is less than 128 or 256, or 55 technically. So it only occupies the first byte, and the next 3 bytes are always just 0 in this case. Then we have a couple of bytes that are reserved for UTF-8 encoded localhost. And if you look at the numbers, they are straightforward the different character values in ASCII because they're all within the ASCII range. And then the last byte is just a single 1, which is true. So this code works, but it was a bit tricky down here. The only reason we were able to figure out how many bytes we need for the address is because we knew how many bytes these two will be taking. There are a couple of other things we have to look out for. For example, the order. I can't just flip these around. I mean, okay, right now I can, but I can't read the FPS from the first few bytes and then read the boolean from the 5th byte and then read the address from the rest. When serializing up here, we have very strict limits on how the data is represented in our stored byte array. This is an exact schema that provides every single value, very specific positions in the final byte array where they are stored. And I have to know the exact order and size of everything to restore the data, to deserialize. So there's no room for errors. If I'm off by even a single byte anywhere, it will break everything. For example, if I make a miscalculation and think, oh, this is actually taking 2 bytes, well, everything will break. We can try that, no? If I think for some reason this boolean will take 2 bytes, well, then I have to do 6 in here and 2 in there, and let's see what happens. Oh, it's local host, not local host. Well, at least it's still single player only true. Okay, let's change the value a bit here. This is now false. Oh no, it's still true. Because this boolean is read from the last byte that contained actually the t, which is greater than 0 in the byte array. So it's interpreted as true. It can get worse. We might actually read in the opposite direction. I think this takes less space, so this would be just straight out length. This would be 4. Well, this now fully breaks, because the boolean can't be read anymore. And even if that could be read, I'm just taking this. Can I actually jump over? Just assume false. Well, this value is a bit weird. I suddenly have the null terminator in the end, in the string for our address, which isn't the correct value. But we read a byte 0 when we try to decode it using the UTF-8 encoding. So precision is important. You cannot mess up. You need to know exactly where every single piece of data is and how much space it's taking. And sometimes you cannot know that. So right now, there's only one unknown, the total length of this address string. That means knowing everything else and knowing the total length, we can still infer that indirectly. We can still calculate that. Let's add a player name. So, now we have two strings. We can still serialize, that's fine. Address bytes, let's call it name bytes, player name. Just gonna add name bytes dot length. And we add the bytes and then name bytes dot length, like that. So this was serialized just fine. Deserialization is a bit of an issue now. I have no way anymore to figure out how many bytes the address is, or the name. I just don't. I know how much they take up in total together, but that doesn't really tell me how much the address is and how much the name. Which characters, if I find them, still belong to the address, and where does the name start? So basically the slightly simplified. It's like this is in the memory and we have to figure out which part of this is the address and which part is the name. I mean, we know it's this, and it's pretty clear to anyone that's reading it, but it's not necessarily that way. I mean, even if you think, oh, this makes more sense, keep in mind that someone might have accidentally input something wrong. Maybe your name is actually this, and for some reason someone put in garbage for the address. You don't know that. You can't be sure of that. So we can't deserialize this anymore. We need more information. So far, we've only input the data we directly need for our different values. But to make it possible to serialize and deserialize, we have to add a bit of overhead. We have to add at least one piece of information that lets us somehow figure out how much space is used for the address or the name. And there are a couple of ways to do that. For example, you could just put in some kind of marker or just some additional index that tells you at this point is where the address stops and the name starts. A more common way is, well, still that, but phrased differently. How many bytes are used for the address? Straightforward. And we do that with another byte array and address length bytes. And we use bit converter again, .get bytes, and input is going to be address bytes.length. So we're not storing a value directly, we're storing an information about the serialized data of some actual information. So we copy this bytes, and we're starting with address bytes for the address length. Like that. So we're starting with the integer that represents the FPS, an actual value, and then read another integer, or write it, that represents the length of the address in bytes. And then we store the actual address. So when we deserialize, what we can do here is use the bit converter. We know this is going to start at 4, because we know FPS is taking the first 4 bytes, so this is still guaranteed. Address length will now be the actual length of the address. And we know this is another integer, it's another guaranteed 4 bytes, so this will start at 8. And we know the total count will be address length. And so when we read the name, we know it will start at 8 plus address length. So it will start at the same point as address, and then you have to move over a couple of steps for the address itself. And the length will be the total length minus 1 for the boolean, 4 for the FPS, and 4 for the address length. So 9 minus address length. Let's see if that worked. I made a mistake. I forgot to add the length in here. Address. Why do I always put the address? Is that actually a word? Is that a word? Address. Sounds more like a name. Weird. Address. Yeah, that compiled. I forgot to add the breakpoint. Let's check again. And that is the correct value. So with this extra piece of information, we were able to deserialize the data again. That's not needed for serialization, but if we don't add it, we essentially delete information. If we don't add this, we lose the information that separates address and name. So we have to make the actual size of our byte array a bit larger. We can even go further, and if you write your own library, you might decide that every string has to add a length, which doesn't make sense. If you have several different types in here that have variable length, like a string, you can only leave one out to the open for figuring it out through principle of exclusion. Ideally, you add the length for every single piece of data you serialize. Because that way, you have for one regular code, it always works the same way, and you have a nifty little tool to figure out if there were errors. For example, if this address length says I have 10 bytes of data to represent the address, but let's say here, I figure out I get a 10, I need 10 bytes for my address, but the array only has 5 more bytes to go, and that's it. But you know, something is wrong. The data says it has a certain length in total, and you get less data than that. So either the data was corrupt and you read the wrong data, or it was cut short and you're missing something. In any case, it acts like a bit of an error correction. It's more like a sanity check, and it makes the code overall a bit easier if you always know exactly how much a piece of data will be. Either it's gonna be static, like an integer which has a fixed length, or it's something like a string which has a variable length if you serialize it to a byte array, but in that case you add the total length. So you know exactly up ahead how much space is allocated for this value, so how many bytes do you read. There are other ways, of course. You could, instead of storing the address directly, add like a stop character in some way. So instead of storing it just pure UTF-8, you might convert it to a system where, okay, simpler case would be you use only bytes 1 through 255 as actually values representing characters or text data in some way, and value 0 would be a stop character. Essentially, that's how you store text. You always have the option of just telling up ahead, the next couple of X bytes are text, that is the actual text they want to represent, or you just say, here's text, go, and you go until you find a stop character. And there are different systems that use that principle. Sometimes it's based on, we know up ahead how long this text is, so we know how much we have to read, and sometimes it's just, here's text, and we read until we hit stop. It's not that one is better than the other. I personally prefer the total length, but that can actually add a memory overhead in certain cases, because I only have small values right now. They always use 4 bytes to store this one integer, even though my address length will never be more than one single byte could represent. And we could actually make use of that. What if instead of storing this fully, what if we just stored server address directly? Or address length, or the FPS. Let's make it simple for that. So instead of doing this, we just store frames per second. Let's just make a new byte. This is gonna be frames per second. Cast to byte directly. And now the FPS byte length is actually saving us a bit here, because I don't have to rewrite this. I do have to rewrite this though. Serial settings. I don't have to use the bit converter, I just use serialized settings 0. And store that as an integer again. And now I have to count this down. This is starting at 1. This is starting at 5. This is also at 5. And this is at 6. Still works, still stored the data. I saved 3 bytes though. That's one of the advantages if you do serialization by yourself. If you take complete control over everything and you determine exactly how the data is arranged, you can minimize the total space used. If you use a standardized approach that has to deal with all kinds of different situations, you probably have to make a compromise somewhere where it's not possible or just way too much effort to minimize the entire footprint. If we used something like this, the integer itself is small enough to be stored as a single byte. And for the total length, if I want to use the system where I store every string as a combination of its total length and the string itself, and I have thousands of strings, then I have thousands of different integers that are stored just to represent the length. It's all overhead. And if most of my thousands of strings are just a handful of characters, then each of them could be represented by a byte. And that means I save thousands of bytes of space, potentially. It's all very specific though. And usually if you store some settings on a disk and we're talking about a couple of kilobytes, then 1 kilobyte more or less doesn't really cut it, doesn't matter. We have the advantage, we have a very simple settings object that we make completely by hand. So it's not that big of a deal to just change this to a byte and store that as itself. Of course, if you have something large, the other way you would go around it is add a compression. You create the full serialized byte array with overhead if necessary, and then you compress it. If you're worrying about, I have so many wasted bytes which are always going to be 0, well, the compression will take care of that. If you have a lot of just sequences of zeros inside your total byte array, a compression algorithm will be very quick to reduce that to just a handful of zeros, if at all. Depends on the compression algorithm itself. So it's not like it's a big deal, but it's still a cool thing you can do. You can really optimize the footprint and make little changes here and there. One important thing, however, if you write your own serialization, well, this is not important, but it's a strong recommendation from me. Don't store the data directly, add one additional piece of overhead. And that would be and a version number. Always add some kind of header to your serialized data, even if it takes up data, even if it takes a couple of bytes. At the very least, you could add a simple integer or maybe just a single byte that represents a version. And when you deserialize, the first thing you do is just oh, actually, I'll use it as a byte. In the settings, 0 version. So you know, how was this data serialized? What version of your schema or your algorithm was used for that? Because you might serialize the data with an old version of your game. So you have an old version of your game that is still version 1, and you serialize the data and store it on the hard drive. And a year later, the player hasn't touched the game in between, just makes an update to the newest version you've released and tries to load the old save again. And in between, the new version looks very different, with very different settings, arranged in a different pattern. You have new settings, you have old settings are gone, the order in which settings are stored is different, maybe the actual way you serialize and deserialize has changed. Your deserialization algorithm would not be able to understand what the old byte array was like. If you just try to straight up give it the same data to the new algorithm, it would not be able to figure that out, and the saved data is lost, which sucks. If you have, however, some kind of header information that can be very easily read, and in the simplest case, that is just a single version number, even just a single byte would be fine. I tend to use always an integer, so the first 4 bytes are always occupied, which means in my case, usually I have 1 byte with version data and then 3 0 bytes, because I don't have any project which exceeded the 255 version mark, but still. Based on that version, you can now, for one, know beforehand if you can actually understand the version of that data. And for something like, I'm loading an old save data, you can defer to a different deserialization method. Maybe you have the old code still around, you don't use it anymore, because you don't serialize like that anymore, but deserialize v1. And when you read version 1, if version is 1, then return serialize v1. Like that. So you have an old method that can understand the old way you stored data and can deserialize that. And if it's not the old version but the current one, then you use your newest code that matches the way you also write new data. It's similar to how we handle different interface versions for plugins. You always add some kind of backwards compatibility, and that's also important for serialization. The biggest mistake I always make is I write some serialization and later realize, oh, I actually need to change the algorithm a bit, and now it's backwards or no longer backwards compatible, but the old version is already used in the wild. And telling a customer that they have to redo all their settings, no, that's not a good idea. Especially if the customer has paid a lot of money. And figuring out that it is an old version later on is always a pain. There are ways often, but it's still a pain. If you make your own serialization, add some way to figure out how to deserialize. Either by adding a header that tells you exactly what version of what serialization or deserialization should be used, or by making the data itself kind of agnostic to that. Like if you use JSON data, the way you read the JSON is always the same. It's just that the information might not be easy to assign, but it's still a bit better than not being able to read it at all. At least if you use something like JSON, which is structured in and of itself, which comes with a predefined schema that probably doesn't change much, if at all, you have a way to manually at least migrate the data. Doing it completely by hand by yourself directly to a byte array has some advantages. You have full control over everything, you can make it very compact, you can add tons of error correction even. Like, I could add more overhead, including in the header, which includes things like checksums. And that way I can make some error correction happening, which would be a bit trickier if you use a standardized library. Not to say they don't have it, it's just you have to figure out how your library would handle that or how you can add it to them. So yeah, serialization, deserialization. It's an interesting topic. I personally quite like this kind of stuff. Just byte pushing, though maybe not in this specific format. This isn't very pretty. You can make this a lot prettier and a lot more performant. Like, this is kind of ugly, and using all these byte arrays, especially for just the byte directly, that's nah. Just a heads up. Yeah, and then you could use that byte array and put it through an obfuscation stream that will store it on your hard drive. Alright, that's all for today. See you next time.